And welcome to today is Thursday. We are doing chapter 7 today, and the topic of the day is actually going to be energy. Okay, and I just want to remind everybody that we have a survey that is going on. I know I have about half the students from the class responded, so I'm waiting for the other half to basically see what we can do about that time change. So that is one thing that I just want to remind you about that the survey is going to end actually on Monday. So hopefully we'll take the time. It's only 2-question thing. So hopefully we'll have the time to do that and basically fill in your feel about that. Okay, so that is one thing. There are quite a few assignments this week too. Okay, so this is a loaded week because we're going to be done with 3 chapters at the end because we did 2 last time when we met. We combined the 2 of them because they're kind of light chapters. And today was another one. So this week has quite a few things in it. And there is homework. There's also a quiz at the end. So there are quite a few things in there. Okay. That's why I'm not opening the next unit until Tuesday of next week. That is the day when we meet. In which case you will see also the rotational motion. And that's basically where we stand in terms of this content in here. Okay. So there will be a little bit of shuffling of things around for this class to meet this requirements. Okay, so those are the changes that I was making for this class. And so you will see them the minute that they become available, hopefully on Tuesday of next week. Please do ask questions. I know that there are assignments that are type homework where you're supposed to do problems. So if you can't work with one of your peers, or you have issues communicating with peers, or you have question about those, please let me know. And we even can go on a one-to-one basis, and meet. I know tomorrow I have a big meeting starting at 9 o'clock and ends around 1 p.m. But anytime after that, I'm available. Give me about probably an hour or something to get something to eat, but we can meet. Or Saturday or Sunday, provided we communicate ahead of time and I'm not outside of home or something like that, where we can meet and work together on things. Now, if this benefits the entire class, I will ask your permission then to record it for the entire class and basically post it in the discussion sessions, or probably in its own right, so that everybody else will benefit from the discussion. Because sometimes you might have a question and you think that you are the only one struggling with it, but once we post it, other people will be very grateful because they think that, oh, that was actually something I was struggling with, and now I'm glad that it was clarified. So that's basically what I'm asking you guys to do. Of course, you are welcome. We can meet anytime, not necessarily during Friday, Saturday, Sunday. The only thing is you really have to communicate with me at least 24 hours ahead of time, because my classes now, I have a lot of classes teaching them, so it's going to be hard a little bit, but it's feasible also during the other days of the week. Okay, Thursday is really the worst day for me to meet, but any other day would be fine. I understand from some of you that probably are not doing live sessions with the other class, but all of my classes are live sessions, and that's why I'm kind of tied up during the other days. But other than that, please do ask, and we can meet together, or you can meet with your peers and work out those problems. And if you still have questions, please ask them. We don't need necessarily to meet, but you can ask me, go through the question, go with you through it. And again, I answer it to you. And if I think that that's something that is going to benefit everybody, I might hit you guys with a message saying, look, problem so-and-so, this is probably the idea to approach that, and things like that. Question so-and-so, this is how you handle it. Does this make sense to you guys?
Yes.
Yes.
Okay, thank you very much. This is an open invitation. Please take advantage of it. Okay, do not let it lingering in there and think, oh, it's okay, I'm fine. Sometimes it's a good idea to just run things by something, and hopefully it's better. Okay, so let's get going with chapter 7. If I can find it, it should be an open window in here. Where is it? So many things are open in this computer, it's not even funny. Where is it? Okay, I think it's this one, except that it's in the wrong thing. That's why I didn't recognize it. That's why I didn't recognize. So, yep, that's the one. Okay, so the concept of energy is something that we're going to be exploring in this class. One of the things that is really important that for you guys to understand is that it's not like somebody, for example, goes to sleep and wake up in the morning having some sort of an insight. Look, I want to invent something called energy. This is not how it works in physics. Physics, these concepts are sometimes forced upon us. We don't really have a choice in the matter, okay? So it's not like somebody decided, you know what, it's a good idea to do energy today and define work as being force times displacement, and then we are all of a sudden in business, force times displacement as being a dot product. As a matter of fact, the dot product, which is something that is used in vectors, which is the projection of the force along the displacement, that is exactly what the work is, was actually derived from the concept of the work. Work came first, the concept of work. So here is the deal. We know Newton's laws of motion basically help us basically describe a system. So if I have an object sitting in position 1, and later on it's going to be in position 2, and let's assume a force took it from this location to the other location, okay? I know F equals to ma here. Any point in space, any point. So at this instant, when this object, while it's moving, it has a clock, okay? So, and it was looking at its clock and basically marking its location all the time and reading its speed. So basically that is what this object is doing. So it has a clock, so it's a position now, it's a position a little later. So this is later, a little later. And going from here to here, its velocity must have changed so that the rate of the velocity with which it changed is proportional to the force. The force is the one that caused all this mass, okay? That's caused this motion. So, and the person comes in here and say, in light of F equals to ma, it checks, measures the force, measures the change in the rate at which the velocity is changing, knows its inertia, and from here it determines that F equals to ma is the one that caused this change in motion. And it tracks this one all the way along from initial state to a final state, basically, okay? Now, the question that arises is, how does the force do it? I know we answered the question for chapter 6 when we asked how does the force do it on a span of time. Now we're asking the same question, except that in changing location from place to place, okay? So that's why we're allowed, in a sense, to tackle chapter 7. So chapter 7 is an attempt to understand the secret, if you wish, of the force in causing change in motion, which is F equals to ma, but in going from a location in space to another location in space. What we're interested in is the overall, okay? We want to know what's going on from the big picture. It turns out that initially the object might have a velocity, okay? It has a velocity here, and it's going to end up with a new velocity there overall. F equals to ma is changing the velocity at that moment, at that location. We don't care for that. We want the big picture. We don't care about the specific instant. We just want the big picture. It turns out that the kinetic energy, which is related to the velocity, by the way, 1/2 of the mass times the velocity squared, okay, changes from a value in here to a value in there. So there is a change in velocity in such a way that this force actually works. It does work. So the force works to change the kinetic energy. That is the answer to the question. So that's why we needed the concept of work, because we had to find that basically a relationship between these two concepts. This 1/2 came to us, was forced upon us. We didn't really have a choice in it. And it's because of this square in here, actually. Because if you take rates, you have 2 times rates that cancel this one, and that's going to give you the A in here. So there is a one-to-one relationship between this one and F equals to ma. Okay, there is a correspondence between these two. Actually, there is a connection between these two, and the 1/2 is exactly what is needed to make this one work. So that is really what is known as the work energy theorem. This thing is the work energy theorem. Forces do work, and in doing so, they change the motion. I'm sorry, they change the kinetic energy, okay? Or the change in the kinetic energy is equal to the work the force does. So that is basically in the same token. So we're going to introduce the concept of energy because it's needed, okay? The concept of work because it's needed. We're going to connect the two in here. We're going to introduce the concept of power because, let's say, for example, we have 10 pounds of some stuff, okay, potatoes, for example, and we need them to be lifted from the first floor to the second floor. So I can take those 10 pounds and take them to the second floor. That is fine, okay? I did do work. I get paid for it. But it took me an hour to do that. I basically dragged them step by step until I got them there. I did the work. I get paid for the work. There's no question about that. And somebody else takes that 10 pounds and lifts it up in 1 minute. It's upstairs. So now the rate at which work is done has a meaning, and that meaning is power. Obviously, the one who does it in 1 minute can do more work if you ask them to do. So that person has more power than the person that took his sweet time to do the same thing. So that is where the concept of power in here. So it turns out power is the rate at which work is done. These two are connected, but this one is the rate of the work, okay? So for example, the light bulb you go and buy from the store, let's say, for example, it has 100 watts. And another light bulb you go and buy it from the store has 40 watts. But the mere fact that you have a light bulb doesn't mean anything. You just have a light bulb. You have to turn it on and then start burning energy in it. Start basically consuming energy in it, converting electrical energy into visible light, into heat actually too, because if you get your hand close from the light bulb, you feel the heat for it, warm on it, from it, okay? Warmth from it. So the rate at which that light bulb of 100 watt consumes energy at 100 joules for every second, whereas the 40 light bulb will consume only 40 joules for every second. So one of them consumes a lot of energy, more than twice this one, per second. So that is when the power company come and hit you with a bill. It's not that they have a light bulb that they're going to charge you. It's the fact that you turn on the light bulb and the light bulb takes that energy and uses it because you're going to be paying for work at the end. I mean, you have to go and work actually to somewhere else, probably lift so many potatoes, then get paid for it so that you can go and pay the power company because they delivered also energy for you, which you used. So that is basically the concept in here. So that is how power, if you wish, and energy are connected to each other, okay? The mechanical energy is another concept. It turns out that energy can be broken down into several ways. It can appear in different ways. I already mentioned the electrical form, which is electrical energy, which is actually kind of a potential energy. A power company comes to your house and they make a plug in your house and they tell you that plug can run 120 volts, okay? 120 volts is actually potential. It's not really, it's not, you didn't do anything with it. Just the fact that you have the plug there, the power company should not charge you. I know the power company charge for the fact that you have subscription and taxes and all kinds of nonsense, even if you don't use your electricity, but technically they should not charge you unless you start consuming it, okay? Unless you connect it and convert it to heat, for example, to cook your soup, or for lighting, for example, or TV or something like that. So that is what we mean by potential energy. In that case, it's an electrical energy. If you go to the store and buy a battery, that battery has energy in it too. And that energy is actually stored energy in the battery. It's also chemical energy, as a matter of fact. And if you take that battery and put it somewhere and start using it, that is now you're converting that energy into another energy. So this is, again, a potential energy. Okay, so we have the concept of potential energy. However, we usually mean specific terms with this potential energy. We mean the energy of gravitation. Let me tell you an example. I know I have this object, but it's kind of heavy a little bit. If it falls, it's going to cause a lot of damage. So I'm going to use this one instead. So this object right now basically is sitting still. If I take it and lift it up, now it has energy. How do I know that? If I let go of it, it's going to move and convert that energy into kinetic energy, into an energy of motion. Okay? So kinetic energy is the energy of motion. That's the easiest of them all. But in this case, I say that it has a gravitational energy because of the fact that it's being driven by the power of a force of gravity. So this is gravitational potential energy. Spring, on the other hand, has another potential energy. I now have a spring on the other side. Spring also, if you stretch it, has a potential energy. If you attach a mass to it while it's stretched and let go, it's going to compress. So it's going to move the mass, again, converting it into kinetic energy. So spring is another form of kinetic energy, potential energy that we usually are interested in mechanics. I mentioned already electrical energy, which is actually also kind of potential energy that potentially can spin and make something move, namely electrical motor, okay? So those are, again, all of this are forms of electrical energy, of potential energy. So those are the two concepts. Now, in mechanics, the mechanical energy is the sum of the kinetic energy and the potential energy, which is meant with it mechanical potential energy, in this case, specifically that of a spring or gravity. Okay, so this is what we mean by mechanical energy. And then the great theorem, which is the work energy theorem. This is a powerful theorem. This is one of the most powerful theorems in physics that you can know, because it's really similar. It's equivalent. The word I'm looking for in here, equivalent, to F equals to ma. The might of F equals to ma, Newton's laws, which is a very powerful stuff that can solve anything, have an equal. And that equal is this theorem, the work energy theorem. Because if we do the math, you will see that from Newton's laws of motion, you can get to the work energy theorem. And from the work energy theorem, you can get back to the Newton's laws. So they are equivalent. They have the same weight. They have the same, basically, might in doing problems for us, okay? That's why it has a lot of value, if you wish. Then we're going to talk about conservation of energy. Conservation of energy in terms of mechanical systems only. So basically, if a system has if there is no friction, nothing dissipating energy, nothing wasting energy, then in this case, the energy that you start with, the mechanical energy that you start with, is the same ending mechanical energy that you end up with. Doesn't matter, okay? Or if there is no motor, it's the same thing. I'm going to give you an example in here. Some of you probably went on rides, Six Flags or something like that. Why do I draw axis? I don't need axis, just lines, okay? So this is the height. If you go and climb on an elevator or whatever, and you end up in so this is probably how the ride would look like, okay? Just making it into a simple version of it, okay? And you ride a car in here. So this is how much potential energy now you have. This whole thing is potential energy, and the car is not moving at this point. And you're sitting on it. Then once it comes down, it's going to lose potential energy because it lost this much. In doing so, it's going to move faster and faster. Hence, it's going to gain a lot of kinetic energy. This is how much kinetic energy it has. The sum of these two is the initial mechanical energy. So again, this is a mechanical energy because this is a kinetic energy and this is a potential energy. The sum of the potential and kinetic is what we call mechanical energy. So the mechanical energy at this point is the same as the mechanical energy you start with. Here, you had no kinetic energy whatsoever. So the kinetic energy is actually equal to 0 when you start with. And all of the energy is just potential. At some point, you're going to be moving so fast, gaining kinetic energy, losing in the same time potential energy, but the sum stays the same, constant, provided there is no waste of energy, there is no friction. or the car does not have an engine. If the car has an engine, an electrical engine or whatever, any engine or whatsoever, it can supply more energy to it. So the car can actually move faster than the available energy in this case. And that is because you're pumping energy to the system. As long as you don't have these two kinds of forces, the ones that waste, the ones that pump energy to the system, the energy is conserved. That is basically what this principle is. Then when I look at the machines, okay, machines are useful in a sense that they help us do work, okay? Machines help us do work. And actually there are 6 simple machines. There is the wheel. It helps us, the wheel in a sense, it helps us change the direction of the work, of the force to do work, okay? We can't do work in one direction, so we do it in another direction. There is what? The pulley, which is another, does the same thing. There is the wedge, that includes actually the, and then there is also the lever, which is another simple machine. And then there is the incline, which helps us do work. So all of these machines, they help us do work. That, I mean, by changing the effort, okay? So it's not like we're gaining energy from them. So those are the things that help us do work. It turns out every machine has an efficiency. How efficient is the machine is in terms of how much it really needs energy to do work, okay? There is no 100% efficient machine. All of the machines, their efficiency is less than 100%. How close it can get from 100% machine, that is actually what is useful for it. That's why we define the efficiency of a machine, okay? There is another thing also called the mechanical advantage of a machine, and the mechanical advantage of a machine, how little of an effort you need to do the same work. So you want to do it with the least effort. But don't confuse that with how efficient the machine. The machine can never be 100% efficient, as a matter of fact, always less than 100% efficient, okay? So this is the stuff that then we're recycling of the energy, how the energy basically goes through its life cycle. And the energy for life, in this case, in usually the biosystems and the sources of energy, it turns out that the sun is the vast majority of the energy on the earth, and that includes oil and carbon basically based energies, because of the fact that those relied on the sun at some point to convert energies into different chemical form, and that is basically how the energy is consumed on Earth. There is another source of energy that is probably not coming from the sun, and that is actually the nuclear force or radioactive materials and things like that. Those are actually of an origin that is not the sun. Everything else is the sun, okay? So this is the chapter in a nutshell. Okay, a combination of energy and matter make up the universe. Energy, movers of substances, both a thing and a process observed when it is being transferred or being transformed, a conserved quantity. In itself, the energy is not meaningful, honestly, in this sense. I mean, it's like a quantity, and I think I alluded to the fact that it was Du Châtelet who at some point basically resolved the issue that people had, because they theorized, look, if an object is in motion, it has something, they called it an oomph. And they didn't know exactly what that was. They know it has to do with the velocity, but was it proportional to the velocity or the velocity squared? She argued based on the work of somebody else that, look, if I double the velocity, the impact on clay, for example, from a falling object will quadruple. If I triple the velocity, by adjusting the height correctly from where the object drops, the impact, the effect, the dent, if you wish, in the clay is not going to be tripled. It's going to be a factor of 9. So that's when we knew that the kinetic energy, when the object has that oomph, if you wish, it's proportional to the square of the velocity, not the velocity itself. Okay? The velocity turned out to be the momentum. So an object is moving, it has momentum. That we knew from last time. Now, an object that is moving also, it has kinetic energy. And that kinetic energy, as I was alluding earlier, has to have a factor of 1/2. And the factor of 1/2 was needed to reconcile with F equal to ma, to make these two compatible, okay? Not equal, but compatible. 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 I don't know if I spelled this stuff correctly or not. Okay. Anyway, the point being in here is that as long as you have velocity, you have kinetic energy. And you can do work with it. You can change the form of the clay, for example. You can destroy stuff with it. You can do things. So now an object that was sitting still, for example, that has some chemical energy stored in gasoline, for example, and if you ignite it somehow, that can cause objects to fly every which way, converting whatever energy it has into now kinetic energy. And this kinetic energy, you can do stuff with it too. You can convert it to anything else. So that is basically what the concept of energy comes in. It's usually shows itself during a transformation. Okay. Here, this statement in here, matter and energy, is sometimes alluding to something that we're going to see later on in relativity, and that is a relationship of Mr. Einstein that you were going to see later on, in that matter and energy are essentially the same thing. So this is actually a step for the next few chapters down the road, where matter, like for example, like kilogram of stuff, and energy are the same thing, because this is just a number. C squared is just the speed of light, okay? So matter and energy are the same thing, but in this sense, still, what is energy, which then confuses a little bit the things with matter, is what is matter. It's again, will appear, will show itself when there is transformation from one form to the other. Case in point, drop an object from a height. I say that this object has a kinetic energy, because if I put an object in here, it's going to cause damage to it. It's going to change it. It's going to do stuff. As a matter of fact, if I go to a falling water, that is same thing as if a rock falling. I can take a turbine, okay, and that turbine starts to spin if this water hits the basically the faces of this one just enough. And as it turns, that turbine, if I put it inside a magnet, and if it's made up of the proper coils, I can collect from it electricity, electrical current. This is actually the turbine. This is how they make electricity in Hoover Dam, for example, okay? Take that electricity and plug it in the wall, and now you have a light and things like that. It's all coming from this gravitational energy. It's the same thing like that ball that fell and damaged the clay. That's the same energy for the falling water in this case. So that is gravitational energy in this case. I say it has energy because I was able to convert it to electrical energy, which I was able to convert it to heat or light, which is another form of energy, okay? Or I can do work with it. I can take that energy and store it in the battery, and take the battery and start driving with it. So that's again energy of motion. So we started with the potential energy of gravity, converted it into kinetic energy, back to electrical energy, back to chemical energy in the battery, back to kinetic energy again, which is somewhere in the process. So you can convert form to form to form to form. How does it show itself? It's usually during transformation between stage to stage, okay? That is basically the concept of energy in here. It's a property of a system that enables it to do work, because that's how it shows itself. If it can do work, that's fine, okay? That is energy. Heat also is another form of energy too. Electromagnetic waves from the sun. Here is the sun, okay? It's emitting radiation every which way, okay? The Earth is sitting in here, collecting some of that radiation that hits it. That radiation travels through empty space. There is nothing between us and the sun. So this is an electromagnetic radiation, which is really not matter at all. Not matter at all. There is nothing that travels, not mass, not 10 kilograms or 15 kilograms or 1,000 kilograms or 1,000,000 tons. This is just pure energy in the form of light. Once it hits the Earth, it warms the Earth. Then we can use it for heat, or we can convert it using solar panels into electricity, or we can do whatever we want to with plants takes it from there and uses it as a form of energy to convert to make sugar actually, and other matter that needs it for its growth, and animals come and eat those plants and everything. So basically the whole cycle of life is dependent on just this waves. We call them electromagnetic waves. And that is light basically. So if you're wondering what is this big word in here, means it's light, okay? Except light in this case is just a very small fraction of the big electromagnetic radiation, because on one side there is the infrared, which is a long wavelength, And on the other side, there is the ultraviolet, which is a very short wavelength. And that is basically what the electromagnetic waves. We happen to be, our eyes are sensitive only to a small range, which is between the red and the violet, okay? But everything else is actually electromagnetic waves. Again, we're gonna get into this one later on down the road, okay? Matter is substance we can see, smell, and feel, and occupies space. So that's basically what our definition right now of it. Again, I just alluded to that connection between matter and energy, and we will see that connection down the road again when we get into that topic. Okay? So that is basically what the energy is, the ability to do work. So work involves force and distance. Is force times distance? This is the equation for it. So if you have a homework problem and you're asked to find work and you know the force, let's say, for example, it's 10 Newton, and it moved the object, let's say, for example, for 2 meters, then in this case, the work is going to be 10 times 2, and that is 20 Newton times meter, or we call this one Joule, actually, in honor of Mr. Joule, okay?
So what was the formula?
Force times distance is the work.
All right, thank you.
Okay, no problem. So I took an example in here of 10 Newton, moving an object 2 meters, basically 2 steps, okay? So if you do that, you're gonna end up with 10 times 2, which is 20. And I was alluding to the unit for it being J, for Joule, okay?
Of
In
course.
honor of
And then when we're using meters, we have to use well, I don't know.
Newton for the force.
Uh-huh.
And the distance.
It has to be meters or kilometers or
Meters, okay?
meters, okay.
This is to get the answer in joules, but you can use other units if you like, okay? If, let's say, for example, you have 50 pounds,
Okay.
you want to move it 3 feet, okay? So the answer in this case is going to be 150 pounds feet, okay?
Okay.
So that's an equivalent unit, so you can convert from this unit to joule, but people in the scientific community and engineering, they use joule. They don't use this one.
Okay.
Okay. So, but the guy probably in Home Depot, he will tell you this.
Okay.
Okay, so that is basically, again, the units I would be using most of the times are the units that are used by scientists and engineers, and those are the so-called SI units. SI units, and SI stands in here for Le Système International, which is a French word which really means international system. That's all. Just flip because the adjective and the noun in French and English, they switch locations, okay? And SI is used even in English now. They call it like this, okay? So, and basically the distance is in meters. That's what that system is. The mass is in kilogram. The time is in second. And the current concept that we will see down the road is in ampere. So this is a meter. This is the unit for the mass, which is a kilogram. The time is in seconds. And currents are in ampere. Okay, so this is exactly what the system is. So that when you see me, I use the letter J, and you go to Home Depot and you tell him I need this many joules, the guy would not understand what you're talking about. Tell him about the energy, then it's force, or torque, for example, because they use a different unit for it. How many pounds per feet? Also, they use two there. So you might need to do conversions for him or her, okay? So you have to have that in mind. So if you're going to be shopping for stuff from Lowe's or Home Depot. K is the kilogram, it's the mass. A is the ampere, it's for the current. We didn't see that yet, okay? We will see it down the road, okay? For the electrical current.
Okay.
Okay, if you open your device, it doesn't matter which, any device that has the power supply at the back of it, like your computer, or I don't know about cell phones or not. Most electronics, they will tell you what is the amperage on it. That is the amps. How many amps does it have? A refrigerator, for example, must have a clear indication how many amps behind the scene it has. I'm trying to find something in here easy to look at. So that is the amps, okay, that they talk about. Good. So the units, most of the time, I'm going to be using this MKSA, which is representative of the SI system. And in that case, the unit for the work is going to be, or the work or the energy is going to be the J for joules, okay? In honor of Mr. Joule, who actually did a very good work that we're going to explore it down the road, namely of how to convert heat into energy. That's his work, actually. One of his work. He did a lot of work in engineering and thermodynamics and things like that. So this is one unit that was named after him. Okay, so two things occur whenever work is done: application of force and the movement of something. So you need the force and you need it moves, okay? The key thing in here, the direction of motion and the force must be in the same direction. If the force happened to be like this and the displacement is like that, so this is the displacement. Let's say, for example, the 2 meters was here and the force is here. Not this entire 10 Newton will matter. Only this amount of it, this component of it will matter. So it's really the force in the direction of the displacement, not just any force. For example, this force that is perpendicular to the displacement does no work. This is a lazy force, okay? This is the boss. He sits in the chair all the time, does no work, and basically at the end expects everybody to do work for him or her, okay? So again, this is, if it's perpendicular, if it has an angle, it's just the shade in here. So if you take a flashlight in here and project it, this is just what is in this shade in here that contributes to the force, okay? The math-wise is a little bit involved with this cosine of this angle, but who cares about that? All you do is just care about the component of the force in the direction of motion. That's why it took this example, this simple example, because it's easy to understand 10 Newton times 2 meters, okay? If you push against stationary brick wall for several minutes, do you do work? Ask yourself, do you have displacement? Does the wall move?
No.
No.
So do you do work then?
No,
You're
no.
burning off energy, but your progress is zero.
Yeah.
Yeah, so you do no work. I mean, you sweat, but the sweat in there has nothing to do with work, okay? The sweat there have to do with the effort. So this is something that you have to be careful with. If you sign a contract with your boss saying that you're going to hold the wall from moving for 5 hours, and when he or she comes back and tell you, okay, you're done, good. Can you pay me? He says you didn't do no work, because the contract says for doing work. You didn't do work. I can prove it for you mathematically, he will tell you. So make sure the contract state for effort, not work. Okay. Okay. You have to have somebody who's done physics as a boss, okay? And then probably the court might disagree with his definition of work as it's defined in physics. Okay, again, there is no work on the wall. Okay. If you lift, in this case, an object with a given mass, you do work.
How come
Sorry?
for that though it says on the wall? Like the answer is A.
You do no work. Look at this statement. Okay, which brings me to a very important point, and that is item 1 of the discussion. Please, before answering any question, make sure you read the whole question. Sometimes it's tricky. This one is trying to trick you. Look at it. You do no work on the wall. You see the key word in there is no. Andrew. Got it?
So what was the first item for the discussion?
The first item is to read the question carefully because it might be confusing. This one is actually one of them. So whenever you have a quiz or whenever you are faced with a question, please read the question thoroughly before answering it. So yes, absolutely. I mean, because it looks confusing. The statement in it, if you push against a stationary brick wall for several minutes, you look at this and you say, there is no work. How come the correct answer is A? And the correct answer is A because there is a no on the question itself. You do no work on the wall. So my item in here, please read the questions thoroughly before answering. Because sometimes it throws you off and you get the wrong
like
answer.
a tricky question,
Yes, exactly. That's the point of the whole thing. So please spend time. Does this answer your question, Andrew?
Yeah, it does. Thank you.
Okay. Sometimes these things are tricky and they get you right when you're not paying attention and you thought you have it all fully covered. And you walk out of this feeling great. And then all of a sudden, the system marks you wrong on it. Wow, why is it wrong? And then when you think for 2 seconds back on it, man, I wish I had thought a little bit longer about it. So that is the item of the discussion today. Okay. So again, this is the point in here. If you take an object of a given mass, you do work, of course. Let's say, for example, I don't know. This is, for the sake of argument, this is, let's say, for example, it's 50 pounds, 25 kilograms. Okay. And you lift it from this floor to that floor, that's 3 meters. Okay. 25 kilograms, by the way, is 25 times 10, which is 250 Newton. And you lift it for 3 meters, you're doing, this guy is doing work. Okay. This guy is doing work that is force times displacement. Force is 250 Newton times the 3, which gives me what? 750 joules of energy. If you double the load on him or her, then instead of lifting 50 pounds, that guy is lifting 100 pounds, which is about 50 kilograms. Then if you follow the rationale in here, 50 kilogram times 10, this 10 is the G, by the way. This is our old friend G. That is the weight you're lifting. So the force in this case is 500 Newton, and that distance is still 3 meters, okay, from floor to floor. So it's 500 Newton times 3, it's 1,500 joules. Obviously, the work in this case has doubled. So doubling the load doubles the work, okay? This athlete, when they lift the weight, during the stage of the actual lifting, there is work done in this case. But holding the weight in place does not require any work. I mean, there is effort. Muscles get tired because muscles need to exert a force that is equal to the weight while that weight is being held in place. But that's another thing, okay? So if the athlete needs to hold it for 5 seconds in order for it to count as lift, then that there is no work. But during the stage when you lift it up from the ground up, then there is work, okay? And again, I just mentioned the fact that the unit is in Joule, in honor of Mr. Joule. That is in SI. Again, if somebody goes to a Home Depot, they probably have no idea, or Lowe's, they have no idea what you're talking about, okay, when you tell them in joules. Oh, that one, they tell you. Oh, we had it in school, but this is how we use it. And I don't know it about joules, okay? Figure it out on your own, they tell you, okay? I don't know, but this is some of my experience with some of these people in there.
I have a question. You said the weightlifter, if the weightlifter holding the weight for like 5 or 10 seconds, that 10-second no work is done?
No, as long as there is no lift up or down while you're holding an object like this, even for an hour, okay?
Okay.
There is no work in here, there's effort. There's a distinction between the two. I want you to make a clear distinction. Because if there is no displacement, there is no work. Remember, it's force times displacement. Lifting it up from the ground up to this point, yes, there is work. I agree with you 100%, up to that point. Then holding it for an hour, if you like, or 5 minutes or 5 seconds, there is no work during that time. There is, the person gets sweaty and tired and all of that, but that's a different thing, okay? Because they need to provide the force equal to that force to maintain it in that level. Good?
So
Yeah.
basically there has to be like some type of movement going on for work to be involved?
Distance, not movement. Distance.
Distance, okay.
Okay, so the weight was in the ground. I don't know how many weights. There is 25 kilogram, and there are 2 on one side. That's 50 kilogram on one side, and I see 2 on the other side. That are a total of 100 kilograms. Okay, let's do an example. And this person probably height is maybe what, 2 meters? I mean, roughly. Okay, you're not gonna tell me it's 1.76, 176 centimeters. Okay, probably you're right. Okay, but they need to hold it a little bit above their head in order to count as a lift. So it's gonna travel 2 meters. So we're gonna figure out this thing in here as we speak. It's a 2 meter height. Okay, lifting it from the ground to that point. Okay, now we are looking at 100 kilograms. You guys see 100 kilograms in the picture because there is 25 on each side. There are 225 on each side. So there are a total of 425, which is 100 kilograms, correct? Altogether.
And 40 pounds to the bar.
Okay, we're going to neglect that. At 40 pounds to it, is it by itself? Okay, 40 pounds, what is that? 20 kilograms. So we're looking at 120 kilogram. Okay. Please don't tell me to add the chalk and everything else because I have no idea how to add those things, okay? But the point being in here, we have 120 kilograms moving a distance of 2 meters. But in order for me to find the force, I have to multiply it by 10 meters per second per second. So this is how much force in this case. It's 1,200 Newton. So when that athlete moved this weight from the floor to the 2 meter bar just above their head, it's going to be this many joules. It's going to be 1,200 Newton times the 2 meters. Okay. Whether they hold, so it's going to be what, 2,400 joules? 2,400 joules. Whether they hold that weight for 1 second and let go, or for 5 minutes, the energy that is spent is 2,400 joules, no more, no less, period, end of the story. Okay. We're done with it. Now, if they hold it for the sake of the timekeepers and the officials in there for 5 seconds or 10 seconds, I have no idea about the rule about this one. They have to basically struggle with it because it's a heavy stuff, okay? And they have to hold it just enough for them to count. But during that instant, during the holding, the object did not move higher or lower to do work, okay? It stayed in the same height. So at that moment, there is no work dispensed, okay? There is nothing. There is an effort. It's clearly, I mean, some people, they cannot hold it for that long, and that's why they disqualify that lift. They have to try again, or I don't know what the rules, but the effort is different because the muscles need to provide the equivalent of 1,200 newtons for at least 5 to 10 seconds, or whatever the rule says, to stay to count. Does this clarify the question for Arfana and also Brandon? I don't know who asked this question, I guess.
Yes.
Okay, very good.
I had another question.
Yes.
This is talking about energy, correct? And I'm guessing work is just a category of energy, because if you were to talk about energy, you would still be expending energy, keeping that up using a stabilizing energy to stabilize that in that position while fighting against gravity.
Okay, you're talking about another thing that is outside of physics, and let me tell you how I understand it, okay? And correct me if I'm wrong. The athlete, while holding the weight, let's say, for example, they didn't lift it, they found it there, okay? So all they did is just move it slightly, okay? Now they have to hold it in place. Or they come in and they hold it, whenever it was holding it, you remove them. Let's say, for example, it was standing on a big stance, and then you come in, okay, come in here, you go and hold them in space, and you remove the stance. At that point, there is no work at all, because there is no 2,400. So there is energy in this case the person has to spend. And that energy actually is the sweat that you see from them coming out. And that is a chemical energy inside their metabolism, basically, whatever, to basically counter that balance. And that is just to provide an effort in this case, okay? Physically speaking, in terms of physics, there is no work, there is no energy. Whatever is happening in there has nothing to do with physics.
All right.
Okay? Because work, the way we defined it, force times displacement. In the second scenario, where this athlete, they prepare the weights for them on a given height, 2 meters high, and you come in, You stand underneath, you put your hands on top of it, and then they remove whatever supporting the two weights, okay? Now you have to hold it in place. That there is no work in terms of physics because it needs this displacement, and there is no displacement in the second scenario. Yes, at least in terms of physics. Okay? But there is definitely effort in physics too, because we know the weight of this object, is 1200 Newton, and this athlete need to provide 1200 Newton to keep this thing in equilibrium from falling. And that is the effort that this athlete need to provide. And that's what makes this athlete sweat. And that's what makes this athlete probably burn internal energy. That is not the problem of physics. The problem of physics is concerned about the work done on this object. There is no work, but there is equilibrium for that object, and that equilibrium needs to counter this 1200 Newton. Okay? Are we clear on the concept in terms of physics or what's going on?
Yes.
Jacob, that was a very good question. Okay, thank you. Okay, so work is done in lifting a barbell. How much work is done in lifting a barbell that is twice as heavy, the same distance? Of course, it's going to be twice. Okay, you double the mass, you double the work, because remember, you double the mass, you double the weight, you double the entire work, because everything is just multiplied by 2.
And what if we double the distance?
Then you quadruple everything. So if you double the weight and you double the distance, then you quadruple everything.
Okay.
Just square the equation.
Yeah, think in terms of the math equation, okay? Always think about it. Okay, very good. We have quite a few slides, which is good. These discussions are good. You do work when pushing a cart with a constant force. If you push the cart twice as far, then the work you do is twice as much, okay? That is the question that you asked, actually, because the distance doubled now.
Yeah.
Okay, the concept of power, I already alluded to it, and the fact that how much work is done going from per unit time. And I already gave an example. For example, if me, and let's take, for example, Brandon's is, at least it is like, is the last one who spoke. Okay. We are tasked to lift 10 kilograms over the next floor, which is 3 meters high. Then you ask how much work we need to do. I can do that 10 kilogram, let's say, for example, in 10 minutes, okay? 10 minutes, that's, okay, let's leave it 10 minutes, that's fine, okay? Okay, so we have 10 kilogram times 10 meter per second to try to find how many newtons that is. That's 100 Newton, and we're lifting up 3 meters. That is 300 joules. So each one of us will do the 300 joules, no problem. But I do it in 10 minutes, whereas Brandon does it in 1 minute, okay? Then in this case, the power that I must have used is 300 joules divided by 10 minutes. And a minute is 60 seconds, by the way. So the 10 and this one and that one and that one, it's going to be about half. 3 divided by 6, that's about half a joule per second. And the unit for the power is watts. I use about half watts. Okay, not even 60 watts like this light bulb, or I don't know, I think this one is less. Anyway, whereas Brandon will do the same thing in 1 minute. That means 300 joules. It's the same work, okay? And in 60 seconds, cancel this one with that one, 30 divided by 6 is 5 watts. Obviously, Brandon has about 10 times more power than I do. So that is why the quantity of power is needed in here, because it tells you how his work is done, basically, as in terms of time, the rate of which work is done. Okay, this is exactly the concept of power, and the power then is how fast work is done, or the rate at which work is done, not performed, done, okay? Because you don't perform work, you do it. Again, there are several examples in here for doing this one. Again, twice the work for the same amount of time, doubling the power. the same amount of work for half the time. That's still doubling the time, the power, and so on and so forth. Okay. So the units for power is watt, and it's 1 joule per second. And usually in the power company they use the word kilowatt, which stands for 1,000 watts basically. And it was in honor of Mr. James Watt, who did a lot of work in this one in here and steam engines and things like that. So a job can be done slowly or quickly. Both may require the same amount of work, but different amounts of, so in this case, power. Okay, I don't know about the impulse in this case. I don't know about the momentum. I don't know about the energy. Work can be done if it's the same amount of work, but with different amounts of power. That means one work can be done less than the other one, in less time than the other one. Mechanical energy is due to position or motion. Okay, there are two forms of energy. The one that is due to motion is called kinetic energy. The one due to position, like for example, if I take this mass and move it up, now it has a new position. So now I say that this mass has an energy position or potential energy, because if I let go of it, it's going to give me, it's going to convert it to kinetic energy. Actually, I see it move. That's why it's kinetic energy. Same thing. Spring, for example, if I stretch it, it has energy of position. If I let go of it, it's going to compress. If I compress it more than what its normal stretching is, then it's going to relax. Again, it's going to move stuff. Okay. Stored energy held in readiness with a potential energy for doing work. That is basically what the potential energy is. Stretched bow, for example, when you pull it, now it has potential to do energy, to convert it into to do work, because you can let go of it and you see, for example, the arrow move, okay, in space, and actually can do stuff, and it can do a lot of damage actually. Okay. Same thing with the rubber band. It has energy. I have some few rubber bands in here that I was working with earlier, but they're gone. So potential energy due to elevated position, that is gravitational potential energy, and I gave several examples of that for elevated water, for example, in a reservoir, for example, to have it come to the faucet for you at the end, coming fast from the faucet, it has pressure, or what is it? A raised jam of a power driver, or anything that has to do with height, for example. Okay. So potential energy, what is it? Equal to the work done, force required to move it upward. So that's basically what we're saying. Mathematically, it's equal to the weight times height. Weight of an object times the height. Okay, this is the potential energy. Not any potential energy due to gravity, gravitational potential energy, gravitational potential energy. This is how we convert waterfall into electrical energy, by taking advantage of how high the water would fall and turn those turbines. Okay, so that is basically the idea behind potential energy. So when the car is lifted, in this case, it has potential energy, because if you somehow remove this piston, the car can fall and convert that potential energy into kinetic energy. On an incline, again, you can gain potential energy. In this case, I don't know how many, 10 Newton. So if we have a 10 Newton ball, which weighs about 100 grams, then in lifted 3 meters, in this case, you have to do 30 joules. In this case, you lift it over 5 meters, but it's still, the height is the same in this case. So it's still the same, all 3 joules actually, 30 joules, I'm sorry. Whether you go this distance or that distance. Here, it's easier for you to do, because the force will be less than this 10 Newton. It's going to be actually this component of the force, because this is where the 10 Newton is going to be, but you're going to find just this much of it. You're not going to find, again, I was talking about the shadow in this case, okay? Here, there is no shadow, so the entire displacement is in the same direction, okay? Whereas in this case, you'll have to find this much component of the weight, which is not the entire 10 Newton, but just the shadow of it, and over the 5 meters. It's going to result in the same amount of work. Going through these steps doesn't alter anything. It's still 30 joules in this case. So this is a simple machine, actually. This incline is a simple machine. It helps you do work by not spending 10 Newton, but rather spending this shadow of it, which is a lot less than the 10 Newtons. But the trade-off in this case is that you have to do the same thing over longer distance. And here, just go 3 meters. And here, you have to go 5 meters. The kinetic energy is this energy of motion. And this is the formula for it. I've been using this one several times now. And 1/2 times the mass times the speed, or the speed squared. This is the formula for it, okay? The 1/2 again was needed to reconcile with Newton's laws of motion. Again, if you double the speed, in this case, you quadruple the energy, the kinetic energy. Must a car with momentum have kinetic energy? Absolutely, because if you have momentum, that means your MV is not equal to 0, which means then its kinetic energy is not equal to 0 too, because this is the only way for this not to be 0 is the velocity is not 0. Since the velocity is not 0, so it definitely has kinetic energy. The difference in here is the momentum has magnitude and direction. It's a vector, actually, magnitude plus direction. Whereas kinetic energy doesn't care about the direction. It's a magnitude. Just like the mass, it's a scalar. It's not a vector. MV, the momentum, is actually a vector. But the kinetic energy is just like temperature, or like the mass itself, or like any other concept that is a scalar, a number. Okay. So this is our famous work energy theorem. The force works, forces work to change. I'm missing a change in here, okay? To change kinetic energy. This is the famous work energy theorem, okay? Here it is. Symbolically, we write it like this. Work equals to change in kinetic energy. Whenever you see delta, that means change, that's all. Work energy theorem is as strong as F equals to ma, and you can apply it in lieu of F equal to ma all the time. But technically, usually it's good for treating distance and velocities, that's all. But it can be used anytime. It doesn't have to be just for this situation. So in here, it's asking you which one is the work energy theorem. Obviously, it's this one. Work of the force is equal to the change in the kinetic energy. Not kinetic energy. That's just the definition of the kinetic energy. This is the impulse momentum theorem, and this is F equals to ma. Okay, so those are different things, but this is the work energy theorem. So when you're dealing with this situation, the most useful one is this one. When you're dealing just with distance and velocity, because you have distance and velocity in this equation.
Is it like initial kinetic energy and the final kinetic energy?
This delta means usually final minus initial, whatever it is you're doing. This delta, for example, it's the same thing. But this one in here for this expression, final kinetic energy minus initial kinetic energy. This delta in this expression for the impulse momentum theorem also means the same thing. Final, except we're talking about momentum in here, minus initial. So this symbol delta is used extensively in physics, which means just a change. And a change meant always with it final minus initial, okay? That's a good question. So this is that symbol, always final minus initial to whatever is next to it. Make sense?
Yes.
Okay, very good. We still have about a lot of slides to go through, so I want to go to the conservation of energy. Hopefully you guys go through these examples in there. So the law of conservation of energy cannot be created or destroyed. It may be transformed from one form into another, but the total energy of never changes of the universe. So when the universe was created or came out to be, it doesn't matter what your philosophy is, the total energy of the universe was the same, never changed, okay? So again, I gave the example in there from going from, for example, the energy of gravity for the water as it falls, it becomes kinetic energy. Kinetic energy is changed into another kinetic energy for this rotation of those coils around magnets, and that motion is actually converted into electrical energy, which carried by big transformers, and those transformers take on the power lines, and the power lines bring them to your home. And those in your home, you can plug your car, for example, and you will have charge your battery. And now the battery has, you converted the energy from potential to kinetic again, to electrical in this case, to potential electrical, to battery, which is chemical energy, which is again another potential, and then you're going to make the car move, and as the car moves, it's going to go into another form of motion, which is kinetic. Some of this, all along, there is a waste of energy in the form of heat, which will going to heat the environment, and that is actually another form of it. So if you count how many joules you ended up with, probably you start from here, let's say, for example, with 10 joules, okay? If you count at the end how much energy really the car has had in here, let's say, for example, you ended up only with, let's be optimistic a little bit and say 6 joules. You wonder, what happened to the 4 joules? Well, it's in here somewhere, and the processes that was lost, and if you tally all of those, you will find 4 joules. 4 plus 6 is exactly 10. Energy is always changing form from one form to the other, to the other, to the other, okay? And whether heat or anything else, so you can still do it, you can still basically convert it back and forth in other forms, okay? So this is basically in a nutshell what that means. In this simple example, I have a change between, again, potential and kinetic. So if I have this weight sitting at this high, I have potential, and we just saw that the potential energy in this case is this weight times this height. So that is how much potential energy in here. So you come and cut it. At that point, I'm losing potential and I'm gaining kinetic. And kinetic will be 1/2 times the mass times the speed squared. So it's going to increase in speed as long as it's going to be from this height to this height to this height to this height until it reaches the bottom. So this is the speed with which it's going to end up. So I take this equation and multiply the mass times g times height, and equate it to 1/2 the mass times the speed squared, and I can find the speed or whatever you want to. In this case, I have converted potential to kinetic, but then when this object stops, when it hits, it's going to, first of all, dig this one in and change the environment in here. So deform the environment, that's also energy. And then there is sound that I'm gonna hear, that is actually also energy. And there is heat in there, that is also another form of energy. So you ask after it stops, hey, it stopped. You said it converted to kinetic, but it's gone now, the kinetic too, because the object stopped. Well, if you tally this little things in here, how much deformation in here, how much, this is deformation, by the way, it's potential energy because it's energy opposition, how much heat was generated, which is wasted, but you can have a thermometer in there and see how much heat was generated. And if you can measure the intensity of the sound, you collect all of those, you'll find exactly what you started with. Okay. So again, this is the situation. Basically, if she pulls on this one, it has 50 joules. And when you release it, you will measure the speed of this bow, I mean this arrow, and you will see that it is 40 joules. And basically, you can convert it to mass times velocity squared divided by 2. You will find it's exactly 40 joules. So you wonder what happened to the other difference, which is 10 joules, where 10 joules probably went to heat this thing in here, okay? Again, we talked about the similarities and the compare. Both of them have v in it. One of them is a vector, the other one is a scalar. One of them velocity squared, the other one, or the speed, and the other one is velocity as a vector. So that is basically some of the stuff in here, how they're related. I talked about already about simple machines and the fact that Machines can, the devices for multiplying forces or changing the direction of forces. So basically changing the efforts and things like cannot create energy, but transform energy from one form, cannot multiply work or energy. So conservation of energy. The work input must be equal to the work output, albeit probably the output work may not be all useful work because some of it may be dissipated in the form of heat, okay? So this is conservation of energy. So a simple machine or a complicated machine or a compound machine, as they are called, do not really create for you energy, okay? Here is a simple machine. This is a lever, okay? So what you do in this case, you have a load. And you have an effort in here. You would want to use the least amount of force to move that one. Well, the effort in this case has to move this whole distance with this much force, okay? Whereas the load in this case moves this distance with that much load in it, okay? You want to lift an elephant? Fine, you can. Find a point of support in this case, and you can lift if you have this long enough, okay? If you have it long enough, you can always lift that. You can lift anything. Was it, I think it was Archimedes who said, give me a fulcrum and give me a lever and I will lift the world. There is no problem with that. You can do whatever you want to, as long as you have this simple machine. Now the work, ideally, this is an ideal situation where there is no waste in it. The little effort times the big force is equal to, times the big displacement is the work that you need to put, must be equal to the output work, which is in this case the big force with the big load times the distance it moves. How good is this machine? How useful is this machine? It's usually used by the ratio of the effort over the load. So this one, the mechanical advantage, is basically expressed usually in terms of how little F is versus how big F, or if you want to, the other way around. So the mechanical advantage in this case is in the effort. But in terms of efficiency, how much useful work can you get out of it from this much energy that you're going to put in it? Usually that number, ideally it's 1. But because of dissipation of energy, because of the losses, usually it's less than 1, okay? So this is one of them, and I listed them in here: lever, wheel, pulley, inclined plane, wedge, and screw. Those are the different kinds of simple machines. There are all 6 of them in here, okay? The pulley redirects the motion, okay? The direction of force, I'm sorry. Instead of lifting an object up, you can actually pull it down. And it's the same thing. And with this one, with a combination of several pulleys, you can make, in this case, a compound machine. You can lift actually engines in the car, in the mechanic shop, the whole engine or transmission. You can lift it just by pulleys. Or one of those big doors, for example, the big bulky doors that you cannot lift by hand. 2, 3, 4 people try to lift it, they cannot. But if you go back with the pulleys, you can lift it easily with just one hand. But you will notice that the chain will have to move so much for just very little motion of the door. Did any one of you experience this kind of doors, or they're now outdated with the electronics things and anything like that? Does anybody? Okay, you guys, some of you know what I'm talking about, okay? So this is the alternative for that person. They can lift the object this way, okay? Okay, the efficiency, again, I mentioned it, how much useful work, which is usually, or useful energy, which is usually less than the total energy. It cannot be more. So this number is usually expressed in percentage, and it's usually less than 1, okay? So machines are not used because of converting energy. You cannot do that. I mean, you can do conversion of energy for all purposes, but not for this one. Simple machines are used for the effort, for less effort, basically. Like an incline, for example, it's much easier to go on an incline than to shoot straight up. I mean, you can go from the ground all the way to 7th floor if you can somehow walk on the wall. You can, or grab yourself through the wall, and basically you can, but it's very tiring. It requires a lot of effort for you and maybe some special equipment for you to do. But if you go on the stairs or an incline, you can go to the 7th floor. Okay, so that is a simple machine in that case. We're talking about mechanical machines. Don't confuse them with the elevator, which is actually not a mechanical machine. And it may use pulleys, which is actually mechanical. They are mechanical. Okay, with recycled, that is basically when you take energy and basically you recycle it again and you use it. This is actually more of an environmental issues than physical issues, okay? Again, in living organisms, they also use energy and they convert energy in systems. And this question is a little bit outside of what we do in physics, but the point for it in here is they're actually essential part of the whole physical system. We cannot have what do you call it? Carbon-based energies, for example, the fuel or anything else without the living organism as part of the cycle for it. Sources of energy on the Earth, for the vast majority of it, is actually the sun. And anything that you can think of is actually solar energy, with the exception of few energies I mentioned already in the beginning, okay? So these are the few cells in here. They use chemical processes to store energies in them. And in this case, actually for the hydrogen cell, this is the hydrogen cell. Yeah, the hydrogen cell. First of all, we need to make hydrogen cells and then store it and use it for cars. At this point, it's still, I know that there are some cars that run on hydrogen, but they're not as popular as electrical cars yet. Anyway, and this is actually a non-solar source of energy, nuclear energy, which is one of the misconceptions about it, is the fact that it may not be safe in terms of the environment, but actually it's not as damaging as other forms of energy. But that's a political debate more than actually engineering or physical debate. Anyway, this is the chapter, your chapter on energy. When we meet next time, we're going to be talking about rotational dynamics, basically rotational motion. And please watch your messages to make sure that we are good in terms of the survey, and please do the survey for us to help this thing happen. Any questions? We still have about 7 minutes, maybe. If not, I'm going to stop the recording. Brandon?
Is there going to be any homework assigned?
Yeah, there should be, hold on. Starting from next week, yeah, there is an assignment, okay? And that is, no, there is actually this week. What are you talking about? There is actually week 2 assignment. I don't know if you have had a chance to go through that. There is a quiz this week, actually, too. And there is another homework next week. Okay?
Okay, thank you.
For
No
week
problem.
2 math homework, you want us to write it down in a paper, then upload it?
Please, yes. Please
Okay.
upload that work. Take a picture of it, okay? And upload it. Or if you want to write it with a paper, that's fine. Or use Word or Excel, or no, I'm sorry, Excel probably is hard to do. Or Notepad or whatever your editing thing, and you say, okay, but please be verbose. Try to describe your solution, okay? Do not tell me problem one, that is probably your question 1, and the answer is 12 or 17 Newton or something like that, okay? You're going to lose points if you don't include units, but you have to be descriptive of what you're talking about, okay? You have to tell me this and this and this to help the grading in terms of making sure that the.
So you want you want us to write the procedure?
Yes. Okay, there is a rubric in there, okay? For each of those questions. I don't know if you have had a chance to go through it or not, but go through the rubric and it will tell you what it takes to get 5 points for that question, what it takes to get 3 points for that question, and if you don't neither, how much you're going to get. Does everybody see the rubric? Or at least some people do see the rubric in there.
So if we use the formula for any math, we need to write down the formula, which formula we use?
Okay. Yes, you need to tell me. You need to display work, accuracy, proper units, and you have to submit the thing by the due time. Please go through the rubric. The rubric is actually, first of all, can anybody confirm to me that you guys can see the rubric? Because I don't know. Right now I'm kind of, yes or no?
Yes.
And yes, okay, very good. So please follow that rubric verbatim, okay? So make it like your check mark, okay? Did I do this? Yes. 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 Then go to the next one, go to the next one, go to the next one. Because I'm going to follow the rubric when I'm grading. So I want you to also follow it too. Okay. So you have all of the questions in there listed from question 1 to question 5. Question 5 has 2 parts in it. So you're supposed to fulfill those requirements. The whole thing is out of 30 points. Again, if you need help, please do not hesitate to ask me or ask your peers. Go to the book, go to Google. I don't mind, as long as you know how to do these things. That's the objective of this. Stuck with it, there is no problem. Let me know. We meet together. If it benefits everybody, we're going to record it and save it for everybody. If it's something like, for example, a minor, do I forget to, did I include the, do I need to put the comma in here or something like that, then it's probably not needed to be recorded. But if it's something confusing about the question or not clear, please let me know, and we probably share it with everybody else if it's there, okay? If you need to work with somebody, that is actually good, recommended. And if you need me to help you in the process, please let me know so that we can do it. You guys understand what's at stake? The purpose of this is not to challenge you or challenge whether you learn something or not, but actually to help you learn it. Yes?
Yes. Yes.
Yeah.
Okay,
Yes.
very good.
Yeah.
So I will see you guys Tuesday of next week at the same time at this point, unless we make some changes.
There wasn't any questions for this discussion.
There was no questions?
Yeah,
was
we
one.
have a question. It was one.
There was one.
One? No, probably missed at the beginning. I'll go over it again.
Okay.
Okay.
Okay, very good. I'll see you guys.
Thank you.
Have a good
No
weekend.
problem.
Thank you.
Recording.
Thank you.